Hello and welcome to episode 10 of the Wi-Fi for Beginners podcast. My name is Nigel Bowden. I'd like to welcome you along to the series of podcasts which is discussing the fundamentals of wireless LAN networking. In each episode we'll be taking a look at a different aspect of Wi-Fi networking to help you build your understanding and knowledge of wireless LAN networks. Each episode is accompanied by a set of slides describing the topics covered in that episode. Although you don't need to review the slides while you're listening to the podcast, they can be useful for reviewing the material that we discuss and provide some visual aids which may help you more fully understand some of the concepts and the equipment that we describe. All recordings and supporting material can be found at my website, which is wififorbeginners.com, where you can find all of the recordings, slides and reference materials which will help you to follow along with the podcast series. Podcast is a series of audio presentations covering the fundamentals of Wi-Fi networking. Hopefully it's in a fairly easy to understand format that you can consume as you're going about your daily commute, travelling, flying, driving, that sort of thing. Give you an opportunity to learn a little bit more about wireless LANs. It's primarily aimed at people who are already involved in the IT industry, probably got some existing knowledge of networking, or could equally apply to people such as students and other people who have got background knowledge around networking theory. I have to assume a certain level of knowledge that you've already got about networking. Things like the OSI 7-layer model, Ethernet switching and routing, things like IP addressing, local area networks, and also assume that you've listened to some of the previous episodes, because we do build on the various topics that we cover episode by episode, building up our level of knowledge as we move through the series. And we are talking about Wi-Fi in commercial and professional environments. We're not really talking about consumer grade home-based Wi-Fi systems in this series. As I said, my name is Nigel Bowden. I'm a UK-based wireless LAN consultant. Been in IT for quite a number of years now, and I've got a few wireless LAN certifications that I've done over the years, and on a day-to-day basis do wireless LAN design, consultancy and deployment of wireless LANs. I'm on social media. You can find me at Wi-Fi Nigel on Twitter, so that's my handle, at Wi-Fi Nigel, and you can find my blog, which is at wifinigel.com. Okay, so on to the topic of today's podcast. We're actually moving into a little bit more advanced RF. Back in Module 2 we covered the basics of radio frequency theory, and in this particular episode, which is episode 10, which is the beginning of our fourth module, the podcast series is broken down into a number of major topics which I've designated as modules, and module 4, which we're moving into now, is a little bit more on radio frequency theory. So in this particular module we're going to do a little bit of a review of what we talked about in module 2, just a little bit of a refresher about our basic RF theory. Then we're going to be talking about RF system basics, a little bit about CSMA CA, which is carrier sense multiple access with collision avoidance, which may sound a little bit familiar if you're familiar with Ethernet theory. We'll be talking about Wi-Fi bands, we'll be talking about the concept of unlicensed spectrum, and we'll also be talking about the concept of channels in radio frequency theory. Okay, so just to review Module 2, we spent quite a bit of time talking about alternating current theory. We talked about the way that an alternating current flows back and forth, moving between positive and negative polarities, and we also talked about the concept of frequency. So if we have one cycle between positive and negative polarity shifts in 1 second, we have 1 hertz. So hertz is the unit of frequency measurement that we use, and we talked about the fact that we have an electric and a magnetic field which are created around a wire as a current flows through the wire, and the electric and magnetic fields combine to create an electromagnetic field. And if we get a frequency which is high enough flowing through our wire, our alternating current is flowing back and forth, and the electromagnetic field is collapsing and being built, pretty high frequency, then the electromagnetic field itself can actually be detected at a distance from the wire, and this gives us an RF transmission, which is the basis of all of our RF system theory. Just to touch on some of the other major points we talked about, As I say, we mentioned frequency being measured in the basic unit of hertz, and we've also got a number of multipliers which we apply to that. If we have 1,000 cycles per second, we have 1 kilohertz. If we have 1 million cycles per second, that's known as 1 megahertz. And if we have 1,000 million cycles per second, that gives us a gigahertz. And we also touched briefly on the way that we actually divide up the RF spectrum from the very lowest frequencies up to the super high frequencies. We actually split the band into a number of designations. We've got the low frequency band, medium frequency band, high frequency, very high frequency, ultra high frequency, and super high frequency bands, and they're very useful for describing the characteristics and uses of different parts of the frequency spectrum. And when we're talking about wireless LANs, we're really looking at the higher end of the frequency spectrum. We're talking about the ultra high frequency band and the super high frequency bands. We also spent some time talking about the characteristics of an RF signal as its frequency increases. We observed when talking about the radio frequency spectrum, as we moved from the low end of the spectrum up to the higher end, then the general distance that an RF signal is propagated over reduces fairly considerably as we move through the spectrum. As we get to the higher end, then RF signals are propagated over much shorter distances. And we also observed that the ability of RF signals to pass through obstructions is reduced considerably as we get up to the higher end of the frequency spectrum. And we can sort of think of this in general terms of RF signals becoming more and more like light in their characteristics as we move up to the higher end of the RF spectrum. It's quite a useful analogy to consider when we're thinking about the high end of the frequency spectrum. And we extended this analogy further when we were considering how an RF source, such as a wireless access point, might propagate its RF energy around a room or a facility. We can perhaps imagine the AP as a light source, and then imagine how the coverage it provides will be very much dependent on how well it can actually be seen at various points around the room. Things like obstructions are going to block RF signals in the same way that they would block light from a light source. We also discussed the important concept of free space loss, and this describes the way that an RF signal will naturally reduce as it travels over a distance, as it moves away from the RF source, and we observe it at distances further and further away from the transmission source. Then the signal that we receive actually reduces naturally, and this can be described by a free space loss formula, so we can actually describe the signal level that we will receive as we move away from the RF source. Okay, so now we're going to spend a little bit of time looking at the basics of an RF system. This is going to provide us with a little bit of context for some topics we're going to be looking at later on in this particular episode. So we've got two basic entities in an RF system we need to consider. We've got a transmitter or transmission station, which is going to be sending a signal, and we've got a receiver, which is a station which is going to be receiving the signal. And there may be several stations, several receivers in an RF system which are actually able to receive that signal. They're actually within the coverage area of the transmitter, and they may all be able to actually receive that particular signal. We've mentioned the term station a couple of times already, and that is any device which has got access to the RF medium. When we're talking about stations in the context of wireless LANs, we're talking about wireless access points or wireless LAN clients. They're both equally considered to be stations on the wireless LAN. They've got equal access to the RF medium. And another very important basic concept that we have for RF systems is that two stations can only hear each other if they are operating on the same frequency. That may be self-evident potentially, but it's worth pointing out. So they both need to be operating on exactly the same frequency to be able to hear each other. If they're actually listening or transmitting on different frequencies, then they simply won't hear each other. If they're single radio systems, as we have in Wi-Fi networks, then they can only ever be transmitting or listening, and they both have to be on exactly the same frequency to be able to hear each other. So just to recap, in a basic RF system, in a coverage area, we've got one station which is going to be transmitting information on the frequency which is in use within that coverage area, within that cell, if you like, if we're referring to access points. And the other station or stations within the coverage area are going to be using their radios to receive that information. So we've got one station using its radio as a transmitter, and the other stations within that coverage area using their radios as receivers. So while we have one station which is transmitting, all of the other stations have to listen. They can't transmit on the same frequency at the same time. In the last podcast we talked about the concept of half duplex mode of operation, and all stations operate in half duplex mode. They can only ever be transmitting or receiving. They can never be transmitting and receiving at the same time. So this is a very important concept which is fundamental to the operation of wireless LANs. We've got this concept of only one station at any time being able to transmit, and all of the stations having to be quiet and listen to what's on the RF medium. We simply can't have two stations talking at the same time, because if they did talk at the same time, all stations within that coverage area would be able to hear both signals, and it would just be a garbled signal that they receive, and they wouldn't actually be able to decode the data from either station. If you're following along with the slides, I'm actually on slide 11 now. I've included a diagram there which shows this basic concept. We've got an access point in the middle of a coverage area, and within the coverage area we've got a number of different stations, which is various tablets and cell phones, laptops, that type of thing. And we're actually showing the fact that an access point is sending some data to one particular station, which is designated as station A, and even though it's actually sending its data just to station A, we can see that all of the other stations within that coverage area are actually able to receive that same RF signal at the same time. And this is because all of the stations within that coverage area are on the same channel, and we've only got one station, which is the access point, talking at any one time. So in this system, it's only once a transmitting station has finished its transmission that another station can actually use that particular frequency. If a station has some data to send, once one station is finished, another one can jump in and start its transmission, but we can only have one station at any time which is transmitting. And a very good analogy for this is a walkie-talkie system, the old press-to-talk system. If you imagine a number of walkie-talkies deployed amongst people in a building, all of the walkie-talkies have to operate on the same channel, but only ever one person can talk at any time. When one person presses the button and starts talking, all of the other stations on the walkie-talkie channel can hear the transmissions, and it's only once that person finishes their transmission, releases the button, that somebody else around the building can take their turn, press the button, and transmit to all of the other walkie-talkies so that they can all hear the transmissions. So it's a very good analogy. It's very similar to the way that wireless LAN stations operate within the coverage area of a wireless access point. And as we've already mentioned, in radio systems like this, where each station only has one radio, they can only ever be transmitting or receiving at any point in time, so they are inherently half duplex. They can only ever be transmitting or receiving at any point in time, and we can only ever have one station talking. And if we do get two stations which for some reason do transmit at the same time, all of the receivers in the air will receive both signals, and it will just be garbled, corrupted information. And this concept of having multiple stations which are using the channel at the same time is known as Cochannel Interference. It's a very important concept in wireless LANs, and it's something we'll mention later in the series. But if we do get two stations that for some reason are using the same frequency, it can be very disruptive to transmissions within the coverage area of a wireless access point. So we're just going to do a little bit of a recap on Ethernet, just to refresh your memory on Ethernet theory. Hopefully you've heard of the concept of CSMA CD, which is carrier sense with multiple access and collision detection, and this is very much a remnant of the old days of Ethernet theory, when Ethernet was a piece of coax that was installed around a facility, and various stations were tapped onto the common bus, the common piece of coaxial that ran around the building to make their transmissions on the Ethernet system. So we'll just run through the various components of it. We've got the concept of carrier sensing, where the stations that were attached to the coaxial cable were listening on the wire to see if anybody else was transmitting before they actually started sending their data. So that's our carrier sense. The multiple access is the multiple stations which were all attached to the same piece of wire, the same bus, the Ethernet bus that ran around a building. So that gives us our multiple access. And once a station actually started sending its data onto the Ethernet bus, it would monitor the voltage level on the bus. If it detected a voltage spike at the time that it started its own transmission, it could interpret this as a collision, which would mean that another station had actually started transmitting at the same time, and it could abandon its transmission. It would then go through a random back-off algorithm where it would try again after a random amount of time. So if we consider this in relation to the RF systems that we've already been discussing, we've already had this notion of only one RF station being able to transmit at a time, in the same way as we have on an Ethernet bus. So in the same way in an RF system as we have on Ethernet, wireless stations will actually listen before they transmit onto the RF medium. This is a facility known as carrier sense, and the station will listen to see if anybody else is using the channel before it will go ahead and try to transmit itself. So as well as the carrier sense element of things, the similarities with Ethernet don't end there. We've also got this notion of multiple access. We've already talked about having multiple stations in a coverage area which are all able to use the same channel, and as long as all stations take their turn to access the channel, they can all coexist and use the same channel. So this gives us the concept of multiple access in the same way as we had with Ethernet. So far it's exactly the same. We've got the CSMA elements, the carrier sense and the multiple access that we had with Ethernet, but unfortunately with a radio system, as we've already said, it can only ever be transmitting or receiving at any particular point in time. The radio can only be put into a transmit or a receive mode. So when a station actually proceeds with a transmission, it can't actually listen to detect collisions in the air at the same time. So although Ethernet had the ability to monitor the voltage on the Ethernet bus as it made its transmission, we don't have access to the same mechanism in an RF system, because our radio is transmitting and it can't listen at the same time. So in wireless LAN systems we have to use the notion of collision avoidance rather than collision detection. So for Wi-Fi networks, instead of CSMA CD, we actually get CSMA CA, carrier sense, multiple access with collision avoidance. So as we aren't able to detect collisions in a wireless LAN system, we have to use this collision avoidance technique. The way this basically works is that if we have one or more stations that wish to send on the RF channel, the first thing they do, in the same way as we do on Ethernet, is they will listen to see if the medium is available. They will use a carrier sense to detect whether or not anyone else is using the channel. If they actually find that the channel is free and it's available for somebody to transmit, all stations that wish to transmit will actually choose a random number which they will use as a countdown timer. So all stations will select a number and they will start counting backwards from the number that's been assigned. They all use the same interval timer. They count backwards, and the first station which gets to 0 will actually commence its transmission. So it'll start sending its data, and all of the stations that are on the same frequency will be able to hear that transmission, and they will back off and wait until it's finished its transmission before they will then again try to gain access to the medium using this random number technique. So even though we've used our collision avoidance technique, we still have no guarantee that two stations didn't actually select the same random number and count down to 0 at the same time, and they may have transmitted at the same time, causing their transmissions to be garbled when received by other stations. So we need an additional mechanism to detect whether or not a frame sent from one station to another is successfully received. So in wireless LAN networks, we actually require that every frame that's sent is actually acknowledged by the receiving stations. So if a station sends a frame, it will wait until it receives an acknowledgement to verify that it actually arrived successfully. If the station doesn't receive an acknowledgement, it will actually perform a retransmission of the frame to see if it can successfully deliver it a second time. Another important point to note is that wireless access points and clients all have equal access to the RF medium. They are peers on the RF medium. There's no priority for the wireless access point in a wireless LAN system, even though it tends to be the relay point for all wireless client communication across the wireless LAN. It's got exactly the same priority in terms of access to the RF medium as any other stations or any of the clients that are on the same wireless LAN. So just thinking again about this acknowledgement method, this is another overhead which we've got on wireless LAN systems compared to Ethernet. We've mentioned a couple of other overheads previously, so just to recap them, when we're talking about wireless LAN systems compared to Ethernet connectivity, with the wireless LAN network we've only got half duplex transmissions compared to full duplex for Ethernet systems. In a wireless LAN system, only one station at a time can access and transmit the shared medium, whereas on Ethernet systems each station tends to have its own Ethernet port and it can transmit whenever it likes. And also on wireless LAN systems, every layer 2 frame needs to be explicitly acknowledged by the receiving station, whereas with Ethernet systems the frames are just sent and there's no acknowledgement mechanism required. So each of these overheads gives us quite a significant difference in terms of performance between what we might expect from a wireless LAN system and an Ethernet system. If you're following along with the slides, currently at slide 16, and I've modified our picture of an access point in its own coverage area, talking to a number of stations, and just trying to demonstrate here the access point sending a data frame to station A again, and we've got the receipt of an acknowledgement frame from station A back towards the access point to verify that it actually received the data frame okay. If the access point didn't receive the acknowledgement, the ACK frame as it's known, then it would try again, probably several times, until it actually got an acknowledgement from station A to verify that the data frame was received successfully. So you just need to bear in mind this is quite a difference from Ethernet, where we don't have layer 2 acknowledgements. In wireless LANs we have layer 2 acknowledgements which are required for all frames that are sent. So just briefly recapping the access method for stations onto an RF channel. We've already said that only one device at any time may access the channel. If a device, a station, has got a frame to send, first of all it checks to see if the RF medium is free. Then it chooses its random number to perform a countdown to avoid collisions with other stations. Assuming it gets to 0, it actually sends its frame, and then it awaits an acknowledgement by the receiving station to verify that the frame was received successfully. And if we think about this technique, it's a multiple access method, as we've already talked about, but each station on the wireless LAN actually uses this technique, and it's actually got to wait for its turn to access the RF medium. It's a contended medium. The stations on the wireless LAN, when they've got information, they've got data to send, they are actually contending for, they're in competition for the RF medium. And because we can only have one station talking at any point in time, each station has got to wait for its turn to talk over the RF medium. So the implication of this is that all stations on a particular channel have got to share the available bandwidth over the air which is provided by the channel, and this is very similar to the contended medium that we had on the old Ethernet systems. We talked about the Ethernet bus where we've got the coaxial cable running around a building, and we also had the same thing with the old Ethernet hubs, where all stations that were plugged into an Ethernet hub shared a common bus and only one station at a time could ever talk. If we contrast this with modern Ethernet systems, each station has got its own switch port and it may transmit and receive at any time. So the wireless LAN is a shared medium with contended access. And if we just look at a simple example, we may well have a wireless client, maybe a fairly modern wireless laptop that's got a possible connection speed of 450 megabits per second, which is a pretty reasonable bandwidth for any station to have. But what we need to bear in mind is that 450 megs is actually going to be shared with every other client that's on the same AP cell which needs access to send its data. The wireless client itself hasn't actually got 100% of the airtime available to it to use that 450 megabits per second which its uplink could potentially provide for it. We also need to bear in mind that each station on a wireless LAN can only use a half duplex link, so we can pretty much half that 450 megs because we're using a half duplex link. So again, 450 meg potential connection speed is cut in half straight away just because of the half duplex nature of the wireless LAN environment. So you can see that this gives us significant differences in performance between Ethernet networks and wireless LANs. On an Ethernet network, each station has got a dedicated access to the medium and a dedicated amount of bandwidth available. On a wireless LAN, all of the stations share the access. They have to have access to the RF channel, one station at a time, with only one station talking at any point in time, and they're sharing the finite amount of airtime, the amount of bandwidth available over the channel between themselves. So taking these factors into consideration, we generally expect wireless LAN stations to have access to far lower bandwidth compared to an Ethernet network, especially once the wireless LAN becomes busy. If we think of the stations all having to share access to the medium, the more stations we have on the RF channel on the wireless LAN itself, each station has to wait longer to get access to the medium to send its data, so things will be generally far slower compared to Ethernet stations which have got their own dedicated bandwidth available all of the time. Well, that's pretty much it for this episode. We've covered quite a bit of ground there. We've still got a little bit more to cover in this module. We'll be covering that in the next episode. So don't forget, if you'd like access to any of the previous episodes, if you'd like access to the slides that accompany this particular episode, or want information about more resources which can assist you with your wireless LAN studies, please get along to my website, which is wififorbeginners.com, where you can get access to everything there. And there are even a few quizzes that you can have a look at which will quiz you on your knowledge of the last few modules we've covered, and I'll be posting one for this new module soon so you can test your knowledge on RF theory. So hope this episode has been useful to you, and I look forward to joining you again very soon, where we'll be presenting more information on RF theory on the next edition of the Wi-Fi for Beginners podcast.